thanks to the reverse mode accumulation of bird peel penning. After the forward pass propagation works backward along the paths in the computation graph. Normally, each edge denotes a computation, such as a linear transformation followed by a slight nonlinearity. However, there is an advantage in excluding computation on some edges simply using an identity transform instead. A trick that, although as everything under the sun been known for a while, recently rediscovered to be effective in training very deep learning models. In this section, I will walk you through the rediscovery and along the way introduce another transformative concept of gates. It's been conjectured quite early that deeper models should be more powerful than shallow, but we were unable to train them effectively no matter how hard we've tried. Various pre-training approaches, when parameters of each layer are initialized in a smart way, were helping only to a point. The difficulties were discouraging, and we didn't know how to move forward with thin and deep networks. That is until, in 2013, Rich Caruana observed the following effect. What Rich did, let me use some annotation tools here. What he's done was observe in this paper, too deep nets really need to be deep, that if we train a large deep model at the time, and don't quote me on that, I don't remember how deep was that model, maybe 3 to 5 layers, maybe a little deeper, but it was surely wider than I'm drawing, and speech recognition dataset. So after training that model to its entirety, like until convergence and until good accuracy, let's call this model a teacher. What Caruana observed is that if you, in fact, take this output layer right before the softmax, right before the actual prediction, and use this layer as the label, as the target for a shallow network student, or they call them a mimic network, then, and instead of training, this one was trained on a binary target, and a binary target was 0 for those classes that this input doesn't represent, and 1 only for the class the input represents. Again, doesn't matter what it was exactly. Let's say it's a phoneme that is pronounced in the speech, or the whole word in the vocabulary. Not the point. The point is that take this layer of a trained teacher network and use it as a target now for the student network to train, to minimize the discrepancy on the same input data. That is, given an input data x, pass it through a trained network. Instead of returning the thresholded softmax output, take the output layer, use it as your target, and train the student. And voila! The network was powerful, and as powerful in terms of performance as the deep network at the time. So what was happening? Jeff Hinton, called the grandfather of deep learning by some, came up with the explanation, which he termed dark knowledge. And the point was that when you have labels and more when you have labels in your input vector, and this is 1 in k encoding, where k is the size of your vocabulary. So imagine you want to train a model to recognize this particular input. Your model, this particular input, let it be chair. The model works super hard through backprop, back and forth, training with different axes, different labels, different targets, that is, and eventually it learns some regularities in the layer before softmax. When it makes a prediction for the same label that we wanted to return the chair, yes, it does assign 0.9 probability or score to chair, but chair is very close to bench and somewhat, 4 legs, close to a cat, and very far from flower and the car likewise. The point of the dark knowledge, as Jeff Hinton termed it, is that the network did not just simply learn to predict what the model is, what the class of the input is, but it also learned regularities, relations between the classes that it was trained on, which are more likely or more similar to each other. So hidden similarities, or not so hidden. Well, not so hidden for us, but we didn't train the model to be doing that, right? Just a side note also, from this observation, and maybe before that, we started to evaluate our models slightly differently. Instead of just the cross entropy of the best prediction, we're looking sometimes at top k predictions. So sort the scores by the magnitude and look at what did the model think was the first guess, say chair, and what was the second, bench. And down to first guess, second guess by the magnitude of the score that the model assigned, down to k, and then we say the model is correct if our correct class is within the top k. So that's it. Using that, Rich Carana's observation, Jeff Hinton's explanation, Yoshua Benja's group used this to train deep, thin networks, which they called fitnets. So basically, take a large, fat network, but not too deep, 5-10 layers, train it in the backprop manner, and then, well, maybe telescoping should be larger, and then take, say, a 35 layer instead of 10 layer network, and in the same manner use it to train these networks. And these fitnets performed well, they were successful, and well, the most important, they trained through all of that depth despite the vanishing gradients. Yet, for some, this two-stage teacher-student process seemed a bit cumbersome. In 2015, Rupesh Srivastava, Klaus Greff, and Jürgen Schmidhuber made the following, a bit elaborate observation. If we embellish the regular layer in a feed-forward neural network with a transfer and carry gates, we will enable gradients flow along the entire depth of a deep, very deep network. Let's see how they have done it. So first of all, let's re-annotate or redefine our layer, which is usually simply written as non-linearity phi, the element-wise non-linearity of the vector, which is a result of this linear operation matrix of transformation of x. Let's just write it as h of x given w sub h. So all that it's saying is the same. So if we do that, then we can have the following. We can add to this layer, which before was take y, push it through h, and get, oh, what am I talking about? Take x, sorry, take x, push it through h transformation, and get y as an output. So now, what this equation says is take x, push it through t, push it through h, and also push it through c, the carry. C is the carry gate. Why it is a gate, we will cover in just a moment. T is the transfer gate. This solid line says x just goes through. Here where the gating is happening, here where it is happening as well, but for a different gate. Then we add whatever can pass through. Let's be careful here. This is our new x, or if we call it y, and choose a darker color. Then we'll repeat the same block again. So what is happening here? First of all, I want to point out that all I'm doing right now is redundant to this equation. Everything is already written right here. This is Adamart product element-wise. In both cases. So what we're saying is the gates. Well, let's look at what the gates are. Each gate is necessarily a sigmoid nonlinearity after a transformation. For transfer gate and for carry gate, notice a typo here. They're different. Sigmoid nonlinearity just squishes everything from 0 to 1 in that range, 1 and 0. Well, this is, to be precise, this is logistic sigmoid function, not just the sigmoid. So as you remember from our logistic regression, it's that. The output of a transfer gate will be a vector with the values between 0 and 1. When the values are close to 1 or 1, whatever age returns is passed through the gate. That means the gate is open when it's close to 1. When it's close to 0, the gate is closed because no matter what age returns, since it's multiplied by 0, here it's an element-wise multiplication. Nothing passes through. And then we add the original input x untouched. We add the original input x to the result of the separation. If all of the transfer gates are open, they're all are ones, and all of the carry gates are open, they all are ones, then what we're doing is we're passing our x through a layer transformation, but then adding the original x so no information is lost. Kind of strange, right? Well, there is a huge reason to do that, and this is not about passing additional information towards the end of the network. Well, not directly at least. The authors of the highway network paper went the following way. Instead of having two separate, even though they offered that idea themselves, instead of having two separate carry and transfer gates, they suggested an interpolation between the transfer gate and between the gate that passes through the transformed version of x and x. And as you can see here, when this gate is fully open, it's 1, the x doesn't come through, but only the transformed version comes through. When the gate is fully closed, it's 0. The transformation of x doesn't come to the next layer. It's only the x itself passes through that layer. An interesting observation of this is, as I just said, right? If the gate is 0, then x goes to the next level. If the gate is 1, then the h goes to the next level. Then what happens advantageously in this case is that when the gradient, remember this is x, and it flows two directions, through h and by itself to the plus sign. Only there is a gate that governs how much of x will go through and how much of h will go through. When we start differentiating backwards through those units, we observe that this path for the gradient is always available, or almost always available, depending on the gate, because if the gate is 0, then nothing can go through, because it doesn't matter, the past didn't affect the future at this point. But if the gate was open at the times, then there is an information highway, that's why highway networks, such that the gradients can always flow, and the derivative the updates can always be made to the earliest layers in the network, despite the need of propagating the gradient from the start. But what if untrained gate is always open and doesn't let gradients flow? In the beginning, we may be unlucky to initialize it that way. So the suggestion, remember the sigmoid function, it's 0 or open for gradients to flow all the way back when the value of the transfer gate is negative, right? Tends to infinity. So the suggestion is simple. Let's initialize large negative bias. And then eventually the network will, after passing the gradients all the way back, or after passing the error all the way back, eventually the network will train correct transfer gate. So remember, the thing to remember is that our original layer first one goes through the second. This is our original structure of the network. Got transformed into something slightly more complicated, into a packaged version that now has the transformation itself and the transfer gate, but then this is layer 1 and respective parameters, and then layer 2 the same kind of block but with different parameters. Okay, were the results good? The networks that they have trained using traditional layers and highway layers were of depth 10, 20, 50. Right here, 10, 20, 50, and 100. Plain networks, right here, would train increasingly poorly with depth. So this is the shallowest network, this is the least shallow, 10, 20, 50, and 100. Training cross entropy error. For highway networks, the situation is slightly different. Although the overall performance is worse than the 10-layer neural network trained traditionally, the performance of deep networks doesn't deteriorate as badly. So that was very hopeful. And importantly as well, these networks, the highway networks of depth 100, were comparable in performance to fitnets from the previous slide, which were the fitnets were trained by mimicking a teacher. And here, without any tricks with the initialization, just random initialization, the highway trick, the gates that allowed gradient flow backwards in the layers to the beginning of the network, no matter how deep, actually fixed that problem. Now the network started to train. Isn't that encouraging? Right about at the same time, but although it took them half a year, the highway network paper was for half a year online before deep residual learning for image recognition came out. People at Microsoft realized, oh wait, why do we need this? Let me start from scratch. We had this times the gate. Let me just shorthand. And x times another gate. Let's just set those gates to identity, both. And if we do, we get this structure right here. Let me try. Our output y will be ReLU of W2 of another prelude transformation W1 X plus X. So effectively what I written here is exactly the same what's drawn in this diagram. The rhetoric was look, our H, the transformation now of this whole thing is f of x, or what is h of x if this whole unit, including the final value, I guess, is h. Then our f of x is learning to represent residual. I don't know, I think it is a pretty story or a good anecdote to sell the model. But the main reason and the main selling point, not to publish the paper, but to actually why the networks, residual networks took off, is twofold. First of all, this approach that opens up the gates of highway networks still preserves the property of information highway, and that the gradients can flow backwards in time even if they vanish within those layers. And another advantage is that this model is much simpler to think about and to reason through than the highway networks. Although I hope after my explanation, these highway networks and gates are not a mystery anymore and very easy to understand and as easy to train as residual networks if you were to choose to train ones. So another thing to point on this slide, this equation or this expression is identical to this diagram. Why would we choose a diagram representation over a clear and precise mathematical notation? There are multiple reasons to prefer the what I call, and I'm not sure what it is traditional right now, it changes what I call an engineering way of information presentation. Yes, mathematical notation is precise when you need to go down to the nitty-gritty basic principles, but when you need to represent a network with 100 layers, writing it as a formula is unwieldy. Yet, look, we will see now that representing a 34-layer residual network with engineering diagram is still possible. Pardon my putting it on the side. The paper was 2-column and it was space efficient for the authors to make it a thin, long, tall picture. But for me and slide constraint, this is better. Now look here. This is VGG network, similar to AlexNet that we covered in the history of deep learning. It has a few convolutional layers, precisely around 15, right? 12 and 4 are actually 16 convolutional layers, and a feed-forward network on top. Then if we use the same approach and construct a 34-layer network, and notice pooling, there is only one pooling here, in the beginning, where we convolve and downsample the input image, basically by pooling, and then there is no pooling. So if we compare this network, that was the plain network performer in the previous results, with, oh no, take that back. That was about highway networks. You'll see the performance on the next slide. We compare a 34-layer plain network without residual connection and 34 residual network. The only difference is that this identity carrying of the result x through every two layers. Remember my comment about the gradient. When you compute the error here, and when you desire to compute dE with respect to x, what we want is dE with respect to x, and all we can do is dE with respect to the last layer, but then we compute the last layer with respect to the layer before, and so on and so forth. But right here at this inflection point or bifurcation, we will have two gradients. One goes through identity unchanged. Whatever we had here will be right here, and whatever we had here will also successfully, this whole gradient gets through, and will get added and passed through each of those blocks. Even if one block, something bad happens, the gradient vanishes, this gradient that's supposed to come through goes to 0, we'll still be able to pass the gradient to anywhere in the network and continue training. That is an important property of residual networks, as well as highway networks, of course. The results. Turned out, ResNet kept learning and improving with depth. And solid line here is, this is ResNet, this is plain network. They're all CNN convolution. ResNet is convolution. Dotted lines are training error, and solid lines are testing error. Same behavior. The deeper the network, the worse is the error. The larger is the error. With ResNet, it's the opposite. The deeper the network, the error is consistently better. The training error is also much lower, but we mostly worry about generalization error. And that's it. Because of this performance, ease of training, super easy implementation, very easy understanding, and maybe wise marketing with all of this residual rather than vanishing gradients, which all it does. By the way, yes, residual networks, the only purpose and power is in skip connections and gates. Today's not today's, but the topic of this lecture, of this section of our lecture. Now, error surfaces. Let's take all of the parameters of our network, and we will have a billion dimensional or a million at the time dimensional space, and there is an error surface in that multidimensional space that we traverse with gradient descent, and we are trying to get to the minimum eventually, inventing clever tricks with strategies avoiding saddle points and many more. And if you're interested how these visualizations were created, we're in a million dimensional space, how can we get a feel of what's going on? You can look at this, also a recent 2 years maybe old paper visualizing the loss landscape of neural nets. Well, so walking this rough landscape without the skip connections, once added, smooth out the landscape, the error landscape, and convergence becomes much easier. The learning process is much more straightforward. That is the advantage of skip connections. Once the skip connections were there, people thought, wait, why stop there? Why stop at this? We had this dual layers in ResNet and skip connections, skip 2. We had skip 1 in highway networks. But why can't we skip further ahead? Well, how much further? 1 hop, 3 hops, 2 hops, or how many? So, these people, Lawrence van der Matten is one of the authors. I don't remember the others, sorry. Look it up. Or just click here when you get the slides. Just decided, let's take a network of however many layers and add skip connections everywhere. Hooray! Once we have this output, it goes here, and then here, and then here. Once we have this output, it goes here and here. Well, depending on the depth of the function, you get the idea of what we will have, right? And this only goes here. Dense networks. What's the advantage? Let's look at the error surface. The error surface is way smoother than anything we've seen before. So drop a ball here, and the ball will happy roll to solution. Isn't that nice? Good. Of course, that is nice. Notice one thing that I forgot to mention before. Look here. In order for this vector to be addable, or pardon for inventing words, to be compatible with x, element-wise multiplied by something, the dimensions should be the same. And then the output dimension is the same as well. So once we're using residual connections and skip connections, we need to be careful, and we need to make sure that our dimensions are the same. The transformed layer should be the same dimension as the input layer, and that's, I don't know if it's a downside or just a property of using skip connections. You don't always have to keep your entire network the same dimensions, and you'll see when you don't in the next subsection of this lecture, and one of the next subsection of this lecture. But you have to take care and of this correspondence of dimensions. See how all of those dimensions are the same for residual connections to work. Takeaway concepts: skip connections. Why they work? Because of the gradient flow. They preserve or fix the problem of vanishing gradients as much as we can right now. And gates are important as well. We will come back to them when we will look at recurrent neural networks.